ओए, पेन ड्राइव लाया? नहीं। अबे यार, इतने सारे वीडियो लेक्चर्स अब कैसे लूँ? पाइथन सर्वर बना दे। हेलो एवरीबॉडी। Storage devices have been an inherent part of our work culture for a very long time. Be it a college student's necessity for a pen drive or a private cloud owned by a data analytics company, storage devices are everywhere. So let's start by discussing about the types of storage. First type is primary storage. It is also known as main memory or internal memory, often referred to simply as memory, is the one directly accessible to the CPU. The CPU continuously reads instructions stored there and executes them as required. Any data actively operated on is also stored there in uniform manner. The second type of storage is secondary storage. It is also known as external memory or auxiliary storage. It differs from primary storage in that it is not directly accessible by the CPU. The computer usually uses its input-output channels to access secondary storage and transfers the desired data using intermediate area in primary storage. Secondary storage does not lose the data when the device is powered down because it is non-volatile. The third type of data storage is tertiary storage. It provides a third level of storage. Typically, it involves a robotic mechanism which will mount and dismount removable mass storage media into a storage device according to the system's demands. This data is often copied to secondary storage before use. It is primarily used for archiving rarely accessed information since it is much slower than secondary storage. For example, 5 to 60 seconds versus 1 to 10 milliseconds. This is primarily useful for extraordinarily large data stores accessed without human operators. Typical examples include tape libraries and optical jukebox. And the last type of storage is offline storage. This is a computer data storage on a medium or a device that is not under the control of a processing unit. The medium is recorded usually in a secondary or tertiary storage device and then physically removed or disconnected. It must be inserted or connected by a human operator before computer can access it again, for example the pen drives. Now let's discuss the characteristics of storage. Storage technologies at all levels of the storage hierarchy can be differentiated by evaluating certain core characteristics as well as measuring characteristics specific to a particular implementation. These core characteristics are volatility, mutability, accessibility, and addressability. Now we'll walk you through everything related to data storage, from types of storage to their history and evolution from hard disks to CDs. So let's start.
Imagine an airplane flying 1 millimeter above the ground and circling the Earth once every 25 seconds while counting every blade of grass. Shrink all that down so that it fits in the palm of your hand, and you'd have something equivalent to a modern hard drive, an object that can likely hold more information than your local library. So how does it store so much information in such a small space? At the heart of every hard drive is a stack of high-speed spinning disks with a recording head flying over each surface. Each disk is coated with a film of microscopic, magnetized metal grains, and your data doesn't live there in a form you can recognize. Instead, it is recorded as a magnetic pattern formed by groups of those tiny grains. In each group, also known as a bit, all of the grains have their magnetizations aligned in one of two possible states, which correspond to zeros and ones. Data is written onto the disk by converting strings of bits into electrical current fed through an electromagnet. This magnet generates a field strong enough to change the direction of the metal grain's magnetization. Once this information is written onto the disk, the drive uses a magnetic reader to turn it back into a useful form, much like a phonograph needle translates a record's grooves into music. But how can you get so much information out of just zeros and ones? Well, by putting lots of them together. For example, a letter is represented in 1 byte, or 8 bits, and your average photo takes up several megabytes, each of which is 8 million bits. Because each bit must be written onto a physical area of the disk, we're always seeking to increase the disk's areal density, or how many bits can be squeezed into 1 square inch. The areal density of a modern hard drive is about 600 gigabits per square inch, 300 million times greater than that of IBM's first hard drive from 1957. This amazing advance in storage capacity wasn't just a matter of making everything smaller, but involved multiple innovations. A technique called the thin film lithography process allowed engineers to shrink the reader and writer. And despite its size, the reader became more sensitive by taking advantage of new discoveries in magnetic and quantum properties of matter. Bits could also be packed closer together, thanks to mathematical algorithms that filter out noise from magnetic interference and find the most likely bit sequences from each chunk of readback signal. And thermal expansion control of the head, enabled by placing a heater under the magnetic writer, allowed it to fly less than 5 nanometers above the disk surface, about the width of 2 strands of DNA. For the past several decades, the exponential growth in computers' storage capacity and processing power has followed a pattern known as Moore's Law, which in 1975 predicted that information density would double every 2 years. But at around 100 gigabits per square inch, shrinking the magnetic grains further or cramming them closer together posed a new risk, called the superparamagnetic effect. When a magnetic grain volume is too small, its magnetization is easily disturbed by heat energy and can cause bits to switch unintentionally, leading to data loss. Scientists resolved this limitation in a remarkably simple way, by changing the direction of recording from longitudinal to perpendicular, allowing areal density to approach 1 terabit per square inch. Recently, the potential limit has been increased yet again through heat-assisted magnetic recording. This uses an even more thermally stable recording medium whose magnetic resistance is momentarily reduced by heating up a particular spot with a laser and allowing data to be written. And while those drives are currently in the prototype stage, scientists already have the next potential trick up their sleeves: bit-patterned media where bit locations are arranged in separate nano-sized structures, potentially allowing for areal densities of 20 terabits per square inch or more. So it's thanks to the combined efforts of generations of engineers, material scientists, and quantum physicists that this tool of incredible power and precision can spin in the palm of your hand.
Hello, and and welcome to Nerd Sanctum. Today I got a cool topic planned for you guys. I'm going to be explaining everything about how CDs work. Now this includes video games, DVDs, music CDs, and data discs, and also the various devices that we use to read and write data onto discs. Okay, so now let's just jump into the anatomy of how a disc actually is created, right? So basically discs are usually 1.2 millimeters thick. Most of that is a polycarbonate plastic, which is, a clear substance. And then we have, let's say, a thin layer of aluminum, right? That's reflective. Now on top of that we usually put some acrylic solution just to protect the aluminum, and then we have whatever label that you put on top. Okay, now let's talk about the general structure of how we store data onto these disks, right? Imagine if you had a single line or track that starts at the center of the disk and spirals outwards towards the outer portion of the disk. So we have one spiral that contains all the data on a particular disk. So it basically stores this as a series of flat spots or bumps. And a cool thing is actually, if we straightened out this spiral into a straight line, it would actually be about 3.5 miles long, which I find pretty crazy. But anyways, let's look at now how we're using devices to read data from these disks. Most disk reading devices are made out of three main components. You have the drive motor, which actually spins the disk. Then you have a laser and lens pair, which basically shoot a laser onto the disk and figure out whether there's a reflection coming back. And then you have the tracking mechanism, which basically moves the laser and the lens from the inside of the disk to the outside of the disk at the right time, so it can follow that one single file line of data. Okay, so now let's look at how we're actually going to turn those physical bumps on a disk into digital signals that we actually use on our computers. When a disk reading device shoots a laser onto a disk, right, if it hits a flat reflective surface, it simply bounces that laser beam back towards that sensor, and then that sensor picks up that light and says, okay, binary 1, we're getting some signal here, right? Now, if instead it actually hits a bump, what happens is, since that bump's not reflective, it's going to be, going back at a different angle, and that sensor is not going to be able to pick up that signal, so it's going to say binary 0, right? Now you can easily see from this series of flat surfaces and bumps, we're going to get a series of 1s and 0s digitally on our computer. So this binary series of 1s and 0s is going to give us a digital signal. Then we take this digital signal and put it in a digital analog converter, which basically figures out how frequent or how close together these bumps are, right? And then from that closest we can figure out, what total voltage we should put out, which gives us our analog signal, in which we can put in an amplifier to increase the intensity of the voltages and then output to some sort of speaker. How do we deal with things like scratches or dirt marks or dust or whatever, right? Imagine, we can't read every single bump 100% accurately. Now basically how this works is we have two different methods. We have encryption and non-sequential data ordering, which basically means if we're storing data in a single file, right, we can actually put it in different parts of the disk, and then so imagine if we have one scratch, it's going to be fine because we're actually getting that data from a different part of the disk. And another part is, let's say if we poke a little hole in our disks, those bumps aren't even there, right? Some disks have encryption towards the center, so basically what happens is, from the external data or data around that missing portion, it can actually decrypt some algorithm and figure out, okay, well that's what that portion was supposed to be, and mostly fix it if it's not too much of a data loss. Okay, so now that we've explained everything about how to read data from a disk, let's start to discuss how we actually write data to a disk, right? Because I don't see a magical way we could create bumps on this disk. That doesn't really make sense. What chemical engineers did to solve this problem was actually really creative. What they did is they invented a clear dye that, when heated up to a certain temperature, became opaque or not clear. So what happens is, we actually have these devices with these lasers that when they shoot this clear dye, basically what happens is they heat up that clear dye so it becomes not clear. So it's pretty much the same exact thing, but instead of reflective flat spots or non-reflective bumps, we're looking at reflective dye or non-reflective dye. Now, let's move on to how rewritable disks work, right? How does a disk become rewritable? Now, to solve this new problem, what chemical engineers did was they created a dye that changed when it was cooling, right? So imagine if you heated up this dye to a specific temperature, right? What happens is, when it would cool, it would become clear. Now, let's say if you took the same die and you heat it up to a different temperature, what would happen is it would cool down and become opaque. So what you could do is take one laser and shoot it along this spiral pattern along this disc with two different intensities, one making it reflective and the second making it non-reflective, just like the bumps. So that about wraps up every modern technique we have to read and write data.
DRAM. What most people are referring to when they talk about computer memory. Dynamic Random Access Memory is optimized to sit in a sweet spot where it delivers high performance and high density or capacity at a reasonable cost. DDR3 is an example of DRAM, and it's all volatile memory, which means that once you cut power to it, anything stored in DRAM quickly fades away. And on top of that, this is the dynamic part of the DRAM thing, is it's unable to retain data even while it's powered on if it's not being constantly refreshed or rewritten. The good news is that DRAM isn't used for long-term storage, and most of it will be set up for your CPU or graphics processor to use as working memory that contains only the information needed to help them complete the task at hand and nothing more. So these characteristics are not detrimental in any way. Next up is SRAM. This stands for Static Random Access Memory. It's a volatile storage medium, just like DRAM, but the key difference is that it is capable of delivering much higher performance, and that while it's receiving power, it doesn't need to refresh each bit periodically just to keep it from fading. The data will wait instead to be overwritten. Modern high-performance CPUs use SRAM as a way to store the data your CPU needs most right next to it for frequent, fast access. But due to its cost, it's typical for this cache to have a capacity of only a few megabytes. Flash memory, which is a subset of EEPROM, is the first type of memory in our rundown that is non-volatile, meaning that data is retained even when there is no power being provided to the chips. This feature comes with a significant performance reduction and a limited number of program erase or write cycles though. This is a necessary trade-off though, because NAND flash is used to store things like the operating system, applications, and other important data that can't be erased whenever the system is powered down in a consumer PC or device. An SSD is an example of something that uses NAND flash, but in spite of the fact that I just said it has reduced performance, it's still much faster than a more traditional hard drive. The only drawback here is that due to their much higher cost compared to a hard drive, typical capacities for SSD devices are tens or hundreds of gigabytes in, portable devices, or up to 1,000 gigabytes or a terabyte in high-performance computers. NAND flash is also used in low-cost products like USB thumb drives, but the chips used for those are much lower performance and not capable of as many program erasers.
छाया आसमान, देखो झूमता गगन, हे छाया